probability trees. Okay, so like when I put the tree in the background, so I can share that. So right, so tree diagrams. Tree diagrams are a way of representing probabilities, mostly their outcomes, but we include the probabilities on the trees as well. Each branch represents the possible options for the situation. If the events are happening repeatedly, in other words, more than one being taken for a bag, then the branches will continue to form a tree. Okay, so here's my example. Kath makes 2 chocolate rabbits by pouring melted chocolate into molds and leaving them to set. She then removes the molds. The probability that a chocolate rabbit is cracked is 0.1. Draw a tree diagram to show all the outcomes of the 2 chocolate rabbits being removed. Does yours look like this? I do apologise. I don't know what's gone on with it. Alright, so this is our tree diagram. So this is our first branch. Okay, so here we've got, remember the branches represent the options. So the first rabbit is either cracked or not cracked. Yes? Straightforward?
That was scary.
Well, who's at the door? Okay, so it's either cracked or not cracked. So what was the probability that it was cracked? 0.1. Yes, we saw that from the question. So what we do is we write 0.1 on the branch.
Which branch?
The one that goes to the cracked.
But there's also 2 coming from the branch.
Oh, far out, what's the scratch, darling? We haven't got there yet. One step. Yes, 3 steps. The locks, that's lovely. Back. Now, if the probability that it's cracked is 0.1, this branch says not cracked. So what do you think we're going to write here? 0.9. Yes, because we know that probability is add to 1. Okay, that was pretty easy. Yes, we learned that just an hour ago. Now, this portion here represents the second rabbit. Okay? Now, the second rabbit is going to be looked at whether the first one was cracked or if it was not cracked. So that's why you need double branches from both options. Does that make sense? So this was following the path that the first one was cracked. Well, that's got nothing to do with the second one being cracked or not. So we still have 2 options. So our second rabbit can be cracked or not cracked. And then we have to have those same 2 options here. Yes? Now, the probability of the second one being cracked is no different because the question hasn't specified any other probability. So we assume that the probabilities are the same. So again, this would be 0.1. This would be 0.9. This would also be 0.1. This would also be 0.9. Now, whilst it may not seem it, the hardest thing is generally deciding what to have as your options here. Okay? So when we're choosing how to draw them, if they've been partly drawn already, it's great because you can just follow what they've got. But if you're starting from scratch, sometimes that can be the hardest thing. Now, what we do from this is we say, right, we can summarize the outcomes. So this said outcomes, not in your so the outcome. So this would be that they're cracked and cracked. So both rabbits were cracked. Cracked and cracked. Here would be cracked and not cracked. Now notice I write it at the end of the branch. This one was not cracked and then cracked. And then this is not cracked, not cracked. Okay, I like short names that you can write them full on if you wish. B, calculate the probability that both chocolate rabbits will be cracked. So what we do is we go back to our probability tree and we say which options show that they were both cracked. Well, that means cracked and cracked, yes? What did we say about probabilities when there's the and word? Cracked and cracked. What do we do with the probabilities? We multiply them. So we're going to do probability cracked and cracked is 0.1 multiplied by 0.1, which gives 0.1. 0, 1. So there's a very slim chance that both chocolate rabbits will be correct.
Wait, is that a and?
That's an and, yeah.
I thought and was add.
And is as. Oh, sorry, or is as. Oh, God, hard to get it. Alright, work out the probability that one of the chocolate rabbits will be cracked. So we're going back up to here, going back up to our options. One of them cracked. So we've got this option. Does it say at least one or just one? One. Okay, so it's either this one or this one. Yes? Do you see that? So either this one or this one. So we said that to find all probabilities, we add them. Yes? So what we have to do is find the probability of this one, the probability of this one, and then add those two together. Okay? So the probability of that first one, was 0.1 multiplied by 0.9 plus 0.9 multiplied by 0.1. So the first one was cracked, not cracked. Yes, I don't want to keep going up and down.
Wait, is it the crack, not crack first? And then it's what?
So this is cracked, not cracked. That's the first one.
Wait, is it 0.9?
So this was the cracked, not cracked. So this cracked, not cracked first and not cracked. And then we're doing not cracked, cracked. Alright. And then this one was not cracked and cracked. Yes? Are you with me? Alright, so what's 0.1 times 0.9? 9 plus 0.09 gives 0.18 trillions. Okay? That's it. Done.
Wait, can we go back?
Oh, let's see. No, never mind.
You just did see the circle. I don't care.
Wait. Alright, 2 torches.
Wait, you just talking about that thing.
Oh, far out as well. Alright, okay, next one. 2 torches. One red, one black are fitted with new batteries. The probability that a battery lasts for more than 20 hours is 0.7. Draw a tree diagram to show the probabilities of the torch batteries lasting for more or less than 20 hours. Now they've kind of helped you out here because they said more or less than 20 hours. Sometimes people want to go back, we've got 2 torches, one of my branches says red, one says black. Not the case in this situation because what we're interested in is how long the batteries last, okay? So what we do, that clicking's really annoying, is that we start off our tree. Now notice the first branch, if you know that you're going to have additional branches, the first one has to be pretty wide. You can't do it too close, otherwise it's going to get very crammed. But you don't want it too wide that you can't fit anything else in. So this is going to indicate the red torch. Okay, so we're going to talk about the red torch first. So this is going to be more than 20, and this is going to be not more than 20. Okay, 20 or less.
Yes. Okay. Yeah. Wait, more.
What is that?
Yeah.
Will this always be with words?
Yes.
20 or less.
Now sometimes they partially draw the tree for you. You just have to finish it. They're a lot more straightforward, but yeah, there will be lots of words. This is more.
Will we have to ever put numbers?
Oh, no, not really. No. So these are generally descriptions, like because they're saying the probability of things happening. So it could be what's the probability of getting a 6 or not a 6. So you were at 6, not 6. But generally, it's an event that's kind of happening. Yeah.
Could you also write less than 20?
Well, so my question wasn't great because it says more or less than 20 hours. Nothing mentions about the 20. It's a bit like when I said this morning about winning, losing, and there's the fact there's the tie option. So here, this should say more than 20 or 20 or less. So because otherwise we're missing the exactly 20. So that wasn't very well written. So more than 20. So what was the probability that it lasts more than 20? 0.77. I can't see it. I can't remember. So this one would be, excuse me, 0.3. So that's my red torch. But they talked about a black torch as well. So this is where we're going to have our two branches again. So this represents the black torch. And we've got more than 20, 20 or less.
Is that stemming from the more than 20 part?
So yes, it stems from the first branch.
Oh man,
Oh my kitty aunt.
what do I do?
What's the matter?
Look, can I just
Alright, so what we need to do when we're drawing these is to use a pencil here. Because it can go horribly wrong and then we start crying.
Does anyone have whiteout?
Really not.
Emma. What?
Alright, so, and again, is the probability different for the red or black torch? No, they haven't said so, so we're going to assume it's the same. So that would be, again, be 0.7, 0.3, 0.7, 0.3. And our outcomes. It's always good to summarise what's going on here. So we've got more than 20, I'm just going to write plus 20, okay? So we've got plus 20, plus 20. We've got plus 20, and I'm going to say less than or equal to 20. I've got less than or equal to 20, plus 20, and less than or equal to 20, less than or equal to 20. Okay? So there are outcomes. So literally at the end, you're just summarising what we're doing when we follow those branches. So we followed a more than 20 and then a more than 20. That's why we wrote plus 20, plus 20.
What is the point of finding this?
What's the point of finding this?
Like,
Because if I said to you, right, what are the different options? You might say, okay, right, well, one of them could be more than 20, but you might miss one of them. So, for example, the fact that these two are essentially the same outcome, but the other way round. So this is a more than 20 and less, 20 and less. This is a 20 and less and more than 20. So people sometimes think, well, that's the same. But it's not, because this one tells you that the red torch was more than 20 and this one was the black torch and vice versa. So it means that you make sure you include all of the different outcomes. Okay? And then we answer the questions. You'll notice that the questions that we get are very, very similar each time. So find the probability that the battery lasts more than 20 hours in both torches. That's, easy tiger. So that's at more than 20, more than 20. So the probability that it's plus 20, plus 20. How many outcomes does that represent? How many of the outcomes is plus 20, plus 20? Yeah, just one of them, it's the top one. And what did we do when we said we've got that one and that one? Multiply. So what do? We're going to write...
So when do you add?
If you've got more than one situation. No, because this is this and this. So for the type of thing when we add is you've got this and this, or this and this. Yeah? So I forget the numbers again. So 0.7?
Yeah.
Thanks. 0 times 0.7 is 0.49.
0.7 times 0.7.
Yeah. That's what you said. Yeah.
You're
looking at it.
20 equals 0.7?
Yes. So the top branches, Emma,
Yes.
go to the plus 20, plus 20.
Mm-hmm.
And the probabilities on those branches are 0.7, both of them.
Okay.
No, I just don't want to go up and down and still forward, because as soon as I start moving it, it starts going weird. So this one is only one torch, so it's more than 20 hours in just one of the torches. Well, how many outcomes have more than 20 hours in just one torch? Two of them. So this is the situation where we've got ors. Alexis, yeah?
Yeah.
So this is going to be our plus 20, our less than or equal to 20, or less than or equal to 20 plus 20. So that means that we've got 0.7 multiplied by 0.3 plus 0.3 multiplied by 0.7. So that's 0.21 plus 0.21. Now, I have to say it's in these kinds of questions that people tend to make boo-boos in, that they get an answer more than one. Okay, so you've got to be really careful and just use your calculators. If you're not great with multiplying, then just use your calculators. Multiplying decimals, sorry. Sometimes they have fractions here. Okay, so all of these probabilities could be fractions. So you've got to be good and aware about how you multiply and add fractions as well. Now, this one, in at least one torch, you've got a couple of ways that you could do this. In at least one torch means that we've got this situation, or this situation. Yes? Agreed? Now, our prior questions have asked us to find the probability of this one, and then the probability of these two. So actually, in our case here, we could just easily find the answer to this part 3, because we can add these two answers together. Yes? No. So this was our this was the probability of both torches. This was the
I
probability.
just didn't multiply something by something. I don't know what happened there.
Okay. So you can just add these two answers together. So the probability of at least one torch, we can do 0.49 plus 0.42. Yeah?
Because then that's both torches plus another torch.
Because that's the thing, at least one torch. So this was one torch, exactly one torch. This was two torches. So at least one would be either of these options.
What's going on? She's supposed to be like,
I get pulled out of class because I have a thing tonight.
Yeah, and we did. I'm aware.
I'm aware, you
Alright, ladies. So, did we get this now? Yes. Go.
0.91.
So this is 0. Emily.
Sorry.
Later.
Just a quick question.
Yes.
What's the difference between you have to multiply and when do you have to multiply and when do you have to add?
So multiplying is if you want more than one thing has to happen. Okay. So we've got two torches. So because we're talking about two torches, you've got to multiply two probabilities together. Because you're talking about two of the same. Because you've got the red torch and the black torch.
So you multiply it to find the probability
of any event happening. Okay. Now, Natanya, shush! All I can hear is your voice. So, to find the probabilities of any of these events, you're going to multiply across the branches. Okay, so you multiply this and this to get the plus 20 plus 20, so on and so forth. Now, if the question is talking about multiple options here, so for example, the at least one torch, then you're talking about this one, or this one, or this one.
Okay.
So that's where you would add those probabilities together. Now, our questions led us in because we'd found this one, we'd found these two together, so it meant that if we were trying to find all three of these, we would just add those prior answers.
Okay.
Now, the other way is that if you haven't been asked to find those other ones already, and you don't want to have to find the multiples of that, and add them all together, you can say, well, if I want at least one of the torches to be more than 20, It means that I'm interested in everything other than that. Does that make sense? So we want the other three options. So we don't want this. So what we could do is we could find the probability of this one and then subtract that from 1. Why am I subtracting that from 1?
Because probability is equal to 1.
Good, because the probabilities of all of the events happening have to total 1. So if I were to do that, you could do 1, subtract 0.1. No, it's not 0.1, is it? Is it 0.1?
Yeah. No, 0.3.
0.3 multiplied by 0.3. So that's the less than or equal to 20, less than or equal to 20. So that's 1 subtract 0.09, which gives us the same answer. Does that make sense?
Yeah.
Now this green option comes up quite a lot. Okay, so just be aware of it. So the 1 minus something is a lot faster than any of the others, because in an exam they are unlikely to ask you all of these prior questions just to make it easy for you. Okay, so make sure that you do understand this one just because it's a lot easier for you. Because if there were 5 or 6 options there, bless you, and you're trying to find, you have to find 4 of them and not 1 of them, then not 1 of them is a way quicker way of doing it. Okay, let's continue. A bag contains 7 yellow and 3 green marbles. A marble is chosen at random from the bag, its colour is noted and it is replaced. A second marble is chosen at random. Draw a tree diagram to show the possible outcomes for choosing 2 marbles. So, what are my options when I'm going into this bag?
Marble 1 and marble 2.
Okay, so that's going to be my labels at the top, marble 1. Okay? What did you say, Josie? You were right. Yellow and green. Okay, so they are my options for my branches. So marble 1 can either be yellow or green. Yes?
When it says replace, does it just mean put back?
Yes. Okay, that's a fancy pants way of saying put back. But the reason is because in some cases, and we're going to go on to them, they don't put it back. And so obviously if they don't put it back, then probabilities are all going to change. Okay? So marble 1 has got yellow and green. So what's the probability, of getting a yellow marble?
0.7.
0.7. Oh, you've gone to decimal. Nice. Okay, fancy pants. And so either we've got 0.7. If we wanted to, you can say fractions. So what would the fractions be?
It's 7 over 10.
7 over 10. Why is it 7 over 10?
Why?
Because there were 7 yellow marbles, yes? Oh! And we knew that there were 10 in total. Okay? Now, if you are more comfortable with decimals, feel free. If not, stay with fractions. I would suggest that if they are recurring decimals, definitely stay with a fraction. So if they were thirds or sixths or whatever, stay with fractions. Alright, so we've got... in fact, I'm going to stay with fractions for this whole one, just because we haven't done one yet. So what would my green one be?
3 over 3 over 10.
3 over 10. Here's the answer. Oh, shush now. So this is marble 2. Okay, do we have different options or the same options for my marble 2? Same. So I've got yellow, green. I've got 7 over 10 because we put it back, and 3 over 10. 7 over 10, 3 over 10. And so my outcomes are yellow, 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 green, green, yellow, green, green. So you may find this a bit tedious, but I'm hoping you're looking at this saying, well, yeah, it makes sense, I understand, I follow, they're the same for each time. As I said, the main thing is deciding what are going to be your labels on your branches. So for marble 2, it's exactly the same as it was in marble 1. Okay? Find the probability of choosing 1 marble of each colour. Okay, so 1 marble of each colour indicates that we're looking at the probability of yellow and green or the probability of green and yellow? Yes, Hannah.
I'm just wondering for the question of would it tell you to draw a tree diagram, or is that like that's how you learn?
They would normally say draw a tree diagram, or often they will say complete the tree diagram.
Okay.
As I say, they do tend to often start them off for you. So how do I find the probability of yellow-green?
Good question. 0.7 times.
Nice. And then the or tells me we're going to be adding. And then 0.3 multiplied by 0.7.
Why is it always 7 and 3?
I don't know. Just as questions I keep picking. The numbers I keep choosing.
Wait, you have to add them as a or.
Because it's this one or this one. So that's why or tells us we add. So yellow and green, so the and is multiplied, the or is add.
Do you mind just scrolling up for a quick second?
I'll try. Fix.
Thank you very much.
Alright, so next one, two marbles of the same colour. Okay, so two marbles of the same would be the probability of yellow, yellow, or probability of green, green.
Green, yeah.
Yes? So, yellow, yellow, what was the probability of yellow, yellow?
0.7.
And then the or means add 0.3 times 0.3. Yes, Jane?
Could you do this equation with fractions?
Oh shoot, I was supposed to be doing fractions, wasn't I?
you told.
Oh, far out.
Wait, you can just do decimal.
You can, but if this was 7, 10, 3, 10, that's what I want to do, fractions, don't
Yes,
it?
can we?
So this would be, how do we multiply fractions?
Reciprocal.
No.
Oh, never mind.
Just do it. Just do it. Jersey, just do it. But how do we just do it? What do we multiply?
Top by
Yes, top, bottom. Okay, so this would be 21 over 100 plus 21 over 100. We've got our same denominator, so we can just add now our numerators. So that's 42 over 100. In some cases, if you use your calculator to do your multiplying of your fractions, it will simplify them. So if this 21 over 100 doesn't simplify, but if it did, it would simplify and then start changing your denominators. So in probability, probability trees, try and not simplify them, try and not use your calculators to do them, because that will make it a lot easier when you're trying to find multiple solutions. No green marbles. So if you've got no green marbles, what situation is that?
Y.
Just y. So we want probability of y. So that's going to be 7/10 multiplied by 7/10.
We didn't finish 49 over 100. Yeah.
We didn't do what?
Finish the. We just finished the answer. 0.49.
I did, didn't I?
I.
I am totally being told off here. Jersey is just like, woo, I'm a chicken wawa.
58, I believe.
So sorry, Jersey.
Why?
Do it. Do it, Miss Harrison. So I snuck back to fractions.
Hey, why do we need fractions though? Can we just do it with decimals?
You totally can. I'm just trying to imply that.
We'll have a calculator, right?
Yes. Oh my gosh. I wonder sometimes if you're with me or not. So I did have a little side conversation just then, all about fractions, saying that sometimes it's best to keep them as fractions and not use your calculator because your calculator will simplify them.
Oh.
So once they simplify them, their denominators change. Whereas if you keep them as normal, like so if you keep them as unsimplified, it's much easier to then add the numerators.
Decimal, right? It's just better.
Not if they're recurring decimals, no. Maybe. If the denominator is 9, if you've got 9 items, it's going to be... Okay?
It was really cool.
Let's continue. 12:45, I have to finish this.
Yeah.
Alright, this is where...
45.
Yes,
I'm like hungry.
Did we do the no
sampling without replacement. So these are the situations that you are doing something and then the probabilities start changing. Okay? Now, in some questions, in some questions, the not replacement part is obvious. So they will say, I took a bead out and I didn't put it back. Okay, so you think to yourself, oh, hang on a minute, I've now got fewer beads in, so my probabilities have to change. Sometimes it's not so obvious. So for example, you've got a box of chocolates, you take one, you bite into it to decide what flavour, like what's the flavour or whether it's got a hard and soft centre. I would hope that you don't then put it back. Okay? So they don't say you took a chocolate, ate it, and then didn't put it back, because it's implied, yes? Similarly, if you've got cans and none of them have got labels on, and you open a can, you're not then going to put it back in the cupboard having been opened because you've opened it. Okay?
What if you put the lid back on?
A can.
You can't put it back on.
Do you know how cans work? Nothing. Like a can of beans or a can
once you open it, you can't close it.
I guess you can. Yeah.
But no, you can close it.
What about if you put it in a container? Then it's obvious which one it is.
You're thinking too deeply.
You really are. Why'd you have to just drop on it?
I don't know. I honestly thought the cans could have a lid.
Kind of like a can.
Yeah, I know.
Do we need to chat to your parents and get you a kitchen little?
No.
Jesus creepers. Right, or do you just want not eat canned food? Alright, so, as I've said here, we've got chocolates. There's several examples of things that are not replacement that are implied, but, so you just have to think about it. So it's not always going to have a big flashing light saying, P.S. this is not put back. Oh, what's going on here?
But what if you think that it's put it back? For example, what if you put it back, but then it's like saying that you don't put it back?
Then you'll get it wrong. Okay? So, I would hope that it would be one more like this, where they're marbles and they talk about not putting it back or not. Okay? But just be aware that that can be the case. So, a marble is chosen at random for the bag, its colour is noted and is not replaced. The bag is shaken and a second marble is chosen at random. Draw probability tree to show the outcome. So, we've got first bead could be yellow or blue. Second bead, again, could be yellow or blue. So I've drawn the tree for you because for these ones, the important thing is the probabilities. So for the first bead, what would the probability of a yellow one be?
7.
Out of 10. And the blue was 3 out of 10. Now, this is the way that I would complete my probability tree. So I would suggest you might want to consider doing it this way as well. We knew there were 10 beads in the bag for this one. How many beads are in the bag now?
9.
So that means my denominator for each one of them is going to be 9. Okay?
If you use a decimal.
Oh, far out, Brussels
You
sprouts.
don't. Okay.
This is where we go for fractions.
I was using 7.
Okay? So my denominator is now 9. So we say to ourselves, okay, what's my numerator going to be? If I'm following this branch here, it indicates that I had selected a yellow one the first time, yes? There were 7 in the bag, so how many yellow ones are left now? 6. Now, we've got 6 out of 9. So what does that mean that my blue probability would be?
3.
3, because we know
Still the same.
we know that they have to add up to the numerator, the denominator, yes? And also, we didn't take any blue ones out along this branch, yes? So this one is still going to be 3. But the key here is that loads of people change both of them and they shouldn't, which is why I'm trying to get you to put the denominators first, focus on one change, and then say, right, if it's 6/9, this has to be 3/9, because I know that this has to add up to 1. Yeah? Now, going down to this one, this indicates I took a blue one out. So if I took a blue one out, then it means that this number here is now going to be 2, yes? Because there were 3, there are now 2. This is 2/9, this one has to be 7, oh, 7/9. And again, it's 7 because we didn't take any out. That's a 7, that's really not clear.
Clearly.
Yeah? So my outcomes are yellow, 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 blue, blue, yellow, blue, blue. Transviance? So find the probability that both marbles are blue. So here we go. Both marbles are blue means blue, blue. So we're doing probability of blue, blue.
And you don't multiply.
Yes, you do, because we want a blue one and a blue one. What do you mean, come on, sir? Jada, just as a tip, every single one of these we've multiplied. Every one. Sometimes we add as well. So, as a tip, go with multiplying. Multiply. Jada, then if there is more than one option, then we add those answers together.
What do you mean it's blue, blue? That's just
Blue.
the question says.
Am I saying it badly? Like what? So blue and blue. So we would do 3/10 multiplied by 2/9 because I'm following my blue, blue.
Blue in the first speed and blue in the second.
Yes. So follow that branch.
Gotcha.
So they're my two probabilities. So every single question we've done, we multiply them. Every one we've done.
Yeah.
Okay? Now, if there was something else happening, so it was blue or yellow, then we would do the multiplying and then add them afterwards. But in this particular question, it's just multiplying. So, this is 6/90, yes? We've said that we don't need to simplify because it's probability. Bless you, shiver me timbers. Right, one marble of each colour is chosen. So here, we've got the probability,
Yellow, blue, yellow.
oh, okay, yes, yellow should come first. Yellow, blue, or probability of blue, yellow. So yellow, blue was, what's yellow, blue? I can't see it anymore.
Yellow, blue is
7/10 multiplied by 3/9. Or, so or means plus. Blue, yellow was 3/10. Pardon? 7/9. Thanks. So this is where I'm saying that if you use your calculator to do some of this, it starts to get a bit more complicated. It's much easier to just keep it as simplified fractions. So here we've got 21 over 90 plus 21 over 90, which is 42 over 90. See, we multiplied and then added. You getting it?
Yeah, I just wish the question had or in it.
I know, they won't. They're just tricky. Are we good to move on? The tank, you got this down?
Yep.
Yes, quite well. We are doing well. Good job. These are sweets. So the bag contains 12 lemon and 4 orange sweets. Reuben chooses a sweet at random and eats it. Okay? Right. If he eats it, is it going back in the bag?
No.
No. He then chooses a second sweet and eats it. Draw a probability diagram to show this. So this is one of those ones where it's implied, it's not stated. Shush now. Okay, so this first sweet.
She knows Reuben's.
What are my options?
Lemon.
Don't shout once. Lemon or orange? What's my second sweet option?
Wait, did you say first?
Yeah,
Lemon.
sure. What's my second sweet option? Lemon. Orange. lemon, orange. Shush, where do you go? So what was the probability of a lemon sweet for the first option?
12 out of 16.
Is it? I'm believing you. I can't remember how many are in there.
Yeah.
And orange is. Okay. So that second sweet, how many's in the bag? So this is where we do our denominator first. Yes. Try and follow these steps. It really is easier.
Wait, why are you 15?
Oh. I don't mean to be rude, Emma, but try and keep up,
I'm
sweetheart.
trying. You guys are running like.
Are we going? Am I going to
Actually, no. I think I'm trying to still do this. I'm just I'm just dumb. I can't figure.
No, you're not dumb. Don't use that word, please.
We could call them probability.
You're not. So. Amelia's just dying at that. Right. So we've got a denominator of 15. Okay. So if we followed the L for the first root, we had a 12 to start with. How many do we have now? 11. So remember, then what do? We say, right, our denominator is 15, so that means how many orange must there be?
4.
I was going to say 4. Yes? So 11 plus 4 is 15. The second option, we've got orange. So we took an orange out here. So my orange is going to go down by 1, so I'm now going to only have 3. And if it's a denominator of 15, this must be 12. Okay? So here we've got orange, lemon, orange. I can't read all the way at the top. Lemon. So Jada, for every single one of these, we multiply first, yes? So if I want to know about this one, multiply. If I want to know about the top one, multiply. If I want to know about any of these options, we multiply. Okay?
Yeah.
Then if there is more than one thing that we're interested in, we would add those afterwards. Okay?
So when you say more than one, you mean just like
So for example, if I said at least one orange,
there's multiple things.
there are multiple things that have at least one orange.
Ah, okay.
Are you with me now?
Yes.
Okay, good.
Yeah.
Hannah.
Would there ever be like other 3 sweets?
Possibly, yes. Okay? If there is, obviously, you would keep going.
Yeah.
And your denominator then would drop down to 14. And then you'd have to think about what you're going to fit. So, and that's why when you're drawing these, you've got to make sure that the first one's quite wide, because if you're going more, you can imagine if you've got then 2 branches off at each of these, it gets quite busy. Okay, so I would imagine they usually stick to 2. They don't normally go to 3 in your GCSEs. Right, so find the probability of choosing 2 orange sweets. So we've got the probability of orange. What was orange?
4 over 16 times 3.
Okay, now when I say don't use your calculators, I'm suggesting 16 multiplied by 15, use your calculator for. I'm just suggesting don't use it as fraction. Oh, and now Ashley's TikToking. Thank you. So it's 12 over 240. So we actually know that all our denominators are going to be 240. Yes, because the denominators for every single one of those options is 16 and 15. So 1 sweet of each flavour. So 1 sweet of each means orange, yellow. No, it's not yellow. What is it? Lemon, thanks. Or lemon, orange. So that is
4 over 6. Multiply. And then you add.
multiply.
12 over 16. Plus 12 over 16. Wait, where did you get 4?
The thing.
Wait, 4 over 16 times 12 over 15. The orange fruit. I keep reading
Jess like so harsh. But the thing, like, come on,
to do it that way, like seriously.
Yeah, it was kind of weird. You were I apologise. I just went with the so sorry. So 4 times 12 is 48. So we just know our denominator is 240. We just had that discussion. And that's 48. And so we've got 96 over 240. Can you see how easy it is once you've got your denominator to not bother using your calculator to do this? Yeah? Because we don't have to simplify it. At least one orange sweet. So this is one of those situations where we've got 3 options. Now, do we want to find 3 options, or do we want to go the quick route? I prefer to go the quick route, so that's 1 subtract yellow, yellow. Okay, so at least one. Oh, shiver me timbers. Lemon. So at least one orange means that it's 1 subtract the probability of lemon, lemon. Okay, because all other 3 options have at least 1 orange. So we've got 1 subtract, what's lemon, lemon? 12 over
16.
Thanks. So that's 1 subtract 132 over 240. Okay. What do you mean?
Is that because you multiply them?
Oh.
It is, right?
It is.
Likely done. Got it.
Okay. Now, are we happy with this? That we wouldn't need our calculators for this, would we? Because we know that 1 whole 1 would be 240 over 240, correct? Yes? So you're going to do 240 minus 132, which is?
108.
Nice. So 1 whole 1, when we're working with fractions, now you've got your calculator so you can use it. I'm just trying to make sure that you remember rules of fractions as well. So in order to deal with fractions and subtracting and adding, we have to have denominator the same. So if you've got 1 whole 1, remember 1 whole 1 can be any numerator and denominator as long as it's the same. So we're going to choose 240. So 1 whole 1 is 240 over 240. So now our denominators are the same, you're just going to do 240 subtract 132.
Yeah.
Yeah? Last one, yes? Let's get it all done and then we can just practice questions. It wasn't subtle. Alright, conditional probability. Conditional probability is where one thing is affected by something else. Okay, so for example, often traffic lights are timed to that you may find that if you catch one green, you catch a lot of green ones, depending on how far you're traveling. It's just the way they're set. And it could be that anything. It could be anything. One probability is linked to or does affect. So for example, a good one is if you're playing sports. So the probability that you win one match, so if you're a tennis player, the probability of you win one match probably means that you're going to perhaps have a good chance of winning the second one as well. Yes? So if you win one, you're more likely to win the second one.
What if you
No. It's all probability.
Or you're playing against somebody.
So what I'm saying is that the probability of you playing the first one and winning is not going to be exactly the same probability the second time, because it implies if you won, then your chances could be higher, because it means you're perhaps good at playing tennis.
Does it take other factors into account?
Yes, the question will always tell you if your probability. So it will say, if something happens, then the probability changes to this. So there's going to be new probabilities there. So Melissa travels through 2 sets of traffic lights on her way to work. The probability that the first set of lights is red is 0.6. If the first set is on red, then the probability the second set will be on red is 0.9. Okay? So our probability has changed. So in those first ones where we were saying the probability is the same for all of our branches, these ones, not so much. So here we go. Oh, let's try and get it done for everyone to stop going away. So red, what's the probability if the first set was on red? 0.6. So that means not red would be 0.4. Now, then we're talking about the second set. So if they were red, what did the probability become now? So this is 0.9. This one would be 0.1. Now, there was some other information, wasn't there? Because it says in the question, Angel, if the first set was on red, then the probability the second set will be on red is 0.9. If the first set is not on red, then the probability that the second set will be on red is 0.25. So here, not red, the second set would be red, would be 0.25. So it's exactly right. Okay? But it's just reading the question and pulling out the correct information, yes? So the trees are not too bad. I think we've got those stuff that are looking at our options. You just need to make sure that you're putting the correct probabilities above. Outcomes would be red, 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 not red, not red, red, and not red, not red. Okay, the rules are the same. You're looking for, if you want red, red, you multiply them across. If you want not red, or red, red, or any of the top three, you multiply them all and then add them. So what's our question say? Both sets of light red.
No. What the heck? What happened? Did you hear? What was that? What? Yeah. Oh my god.
Wait, we've got 1 minute. Red, red.
I thought it was like a deer.
So red, red is 0.6 times 0.9, which is 0.54. Only one set of lights is on red, so we've got red, not red, or not red, red. I don't know what any of these numbers are now. Who can help me out?
0.6 and 0.4.
Thanks.
0.4 times 0.5.
Thank you. Okay, so that's 0.06 plus, oh, I don't know what that is, 0.1, which is 0.16.
Wait, okay, 0.6. Wow, you did that in 0. Was that 4?
Yeah.
4 times 0.5.
So tomorrow's lesson, we're going to just be working on probability questions for the whole period.
1.6?
Yes? Oh wow!
I